live. So it's, the signal that we can officially begin. So, we are very pleased to have Andy Zeng with us. So Andy is a research scientist at Google. Before Google, he graduated from Berkeley, then spent some time at Princeton, and has done a lot of work, first in affordance-based reasoning in robotics, and then has ventured into many other areas. So I think some of the initial work he did was instrumental in the Amazon Robotics Challenge. And then, many of you might have seen the Tossingbot work, which came out of Andy. And, most recently, I think maybe a couple of days ago, Andy, you uploaded this paper on Socratic reasoning, which seems very cool. So, we are very pleased to have you. And, before I hand it over to Andy, let's also thank Tao Chen for helping us organize this seminar. With that, Andy, please take it away. Super excited to have you here.
Awesome. Yeah, thanks for having me. I'm very excited to be here. And yeah, so today I'll talk about retrospectives on scaling robot learning. And just to set some expectations for the talk, I plan to cover a couple projects, roughly 5 to 10 minutes each. And I think that these projects will, because I think there might be somewhat of a broad set of backgrounds in the audience, I optimized this talk mostly for breadth as opposed to depth, so that most people here could have at least something that they can take back home. And if any of you are unsatisfied by the amount of detail that I go into any one of the projects, yeah, feel free to let me know, and I'm happy to chat more about any of these projects offline. Cool. So I thought I'd start out my talk with a dirty laundry slide, because I feel like some of the things that I'll be listing here are actually symptoms of a larger problem. And I think that I'd like to start off by sort of sharing this not so secret recipe to making a rockstar behavior cloning demo on real robots. And I'm sure that for some folks in the audience who have worked on real robot demos, this might be something that resonates with you all. So step 1, collect your own expert data and don't trust anyone else to make it perfect. I think this is, if I was, for example, collecting demonstrations, I know that the way that I'm collecting the data is going to be very different from the way that my mom collects it. So there's this situation where if you want to get your behavior cloning demo to be the absolute best that it could be, you kind of want to collect your own expert data. Step 2, avoid no action data so that your policy doesn't just sit there. I think the unfortunate truth for many of these demos that rely on a small subset of data is that if any of your subset of data happens to have no actions as output, and this is this plus or minus could be conditioned on your particular state or action representation. But most of the time, if you have no action data in your training data set, then during inference time, your robot, if it lands into a pocket of the state space where it's now predicting no actions and your task is quasi-static, then you're kind of stuck during the inference time. So yeah, avoiding no action data, filtering it out. Step 3, it's not working. Collect more data until extrapolation becomes interpolation. So it's always unclear to me what level of generalization deep nets are able to achieve, especially in the sense that it seems like maybe in order to rather than having the neural net extrapolate, you're instead collecting enough training data so that all of your test time examples fall within the convex hull of the training set. So it's always unclear to me what we mean by extrapolation when we're talking about generalization on deep robot learning. Step 4, train and test on the same day, because who knows, lighting might change tomorrow. Maybe somebody will walk into the lab overnight and accidentally bump into your camera. Your setup just might change tomorrow. And so I think that all of these reasons are just mostly because of you might think of these as hacks for behavior cloning, but I think these are all just symptoms of this core problem, which is that we just don't have a lot of data to work with in the first place. And so we want to make sure that whatever proportion of good data that we have more than the bad data that we have. So one of the projects that, so one of the first things that we did at Google was to see if we can tackle the data problem by ultimately scaling physical robot learning for data collection. And we've got this awesome setup in warehouses where we've got robots sort of lined up, and we've got this amazing rig where we can have operators and machine learning policies sort of connect and remote control these robots in the cloud. through the cloud. And the nice part about this is that you can get a couple thousand episodes on a good week, so you can decently scale. But at the same time, you're still bottlenecked on the rate of data collection because the amount of data that you collect is always going to be linearly scaling with the number of robots that you have. So I can safely say that, with 10 robots, we could probably learn end-to-end pick and place totally fine with objects the size of your palm, because that so happens to fit, your end effector size. But at the same time, it's like if you run into your local VP and you ask, oh, hey, could I get 10x more robots, 10x more dollars, manpower, and space? The VP will be like, either you're crazy or can you actually solve cooking though? And I think that it's for me, at least, when I think of 10x more robots in this case, I think I can say that we can learn end-to-end pick and place we can expand the set of objects that we can do end-to-end pick and place, but I'm not sure if we can actually solve cooking at the level of kind of visual complexity and contact-rich manipulations that's needed there. So, every now and then as a roboticist, you kind of have to pop up a little bit and see what the other fields are doing. And how are they scaling up data collection? You've got computer vision and NLP, and they seem to have really nice internet scale data. And the thing that you'll quickly realize is that they're collecting data, a lot of data, because they just have scripts that that crawl the internet. And these scripts are fully autonomous. They're very easy to scale. You could just deploy a couple thousand on different machines and just aggregate all the data. These scripts, they don't need a robot wrangler to supervise them all the time. These scripts, they don't need to, if an end effector breaks on a script, you'll have to quote unquote fix the end effector. These scripts, they just run autonomously without supervision. And so they have access to all of this internet data. And the main question for me, at least, is that this puts us data collection in these fields kind of in a different regime than robotics, where in robotics, we still have this fundamental limitation. And I think that it's not all doom and gloom, in the sense that I feel like what we need to do is to start thinking about, we can scale our physical robots, but we need to combine it with something. And that's something, I think there are various different options for what that something can be. But at least in the scope of this talk, I'll cover two areas that I'm recently quite excited about in terms of potential solutions that, when combined with scaling robot learning, we might be able to achieve some awesome results. So the first area that I'll talk about, it leans a little bit more into the practical application side, but most of it is making the most out of the data that we already have. And so this ties into using inductive biases of deep networks, or leveraging prior structure about the problem in order to modify your architecture in ways that makes it potentially amenable to the data that you have. And the second area that I'll start talking about as well is how can we learn from the internet? And this, at least, I've had the opportunity to work on several projects that are related to these two areas, and I've divided my talk into two parts. So the first part, we'll talk about making the most out of the data that we have, and then the second part, we'll talk more about how can we learn from the internet. And as Pulkit mentioned, we have a recent paper that just got released, came out on arXiv, I think last night. It's called Socratic Models, and hopefully I want to reserve some time to talk about that project. Cool. So the first project that I'll talk about is Tossingbot. And Tossingbot was a very fun project. We started off by how it came to be was that we were walking in warehouses and we realized that the vast majority of these pick and place robots are executing very rigid motions. And this is very much in contrast to if you walked into a real warehouse and you had human pick and placers doing the task. They're oftentimes sort of gently tossing around. And so that makes you realize that in order to ever achieve human level efficiency for these tasks, you got to start involving dynamics. And so we went back into our lab, and one of the first things that we wanted to try out was, can we get a robot to toss something? Turns out that they can. And in fact, I think that decades of hardware research have really enabled these robots to do these things really repeatably. So this is an example of just, you can take a UR5 and then as long as you're grasping the center of a pen plus or minus 2 millimeters, you're capable of getting very repeatable grasps and tosses. Yeah, so this was one of the first inclinations where we thought, oh, okay, tossing might actually be a thing. So we decided that we wanted to expand the scope of objects for which a system like this could handle. And that was where Tossingbot came in, where we decided to find ways in which we can have the system be able to learn how to grasp objects from the bin and condition on that be able to throw into the correct bin. And this involves some deep learning in the sense that you want to handle the variation in different objects that you can come access to. So one of the first takeaways of the Tossingbot project is that dense visual affordances are great for sample efficient grasping. So we have this setup here where we have RGBD cameras that are capturing a point cloud of the scene, projecting it into an orthographic representation. And the nice part about that is everything is metrically consistent. And then you can feed that into a fully convolutional network to get you grasping affordances. So these are dense per pixel wise predictions of how good a grasp is. Higher means better grasp, lower means worse grasp. And here the higher is hotter regions. And you can think of this architecture as essentially learning a grasping value function, where every grasp is represented by a particular pixel, and it's conditioned on the information that's available inside of the receptive field in the orthographic projection. And one of the nice parts about using fully convolutional networks through all of this is that your spatial action predictions are anchored on your visual features. And so whether it's through, you can have translation equivariance, and is there a question or quite catch that? Okay, well, anyways, translation equivariance, and if you could also rotate your inputs or also your kernel so that you can get rotation equivariance as well. Another takeaway in Tossingbot is that residual physics is great for sample efficient throwing. So depending on what kind of object that you're grasping and tossing, and depending on how you grasp the object, that can result in very different tossing trajectories. And so the idea behind residual physics was just, okay, we know that each of these trajectories are going to be roughly following a ballistic projectile motion. Can we use that to our advantage? And so the way that we do that is we bake that knowledge inside of a physics-based controller that gives us an initial estimate for the throwing velocity that we want to achieve. And then we would have a visuomotor policy essentially learn these residual corrections that are conditioned on where we grasp the object or what the object looks like as input to the system so that it can correct the original action in order to compensate for the object. And a couple quantitative numbers, but the main point here is that if you want to generalize tossing to, say, new locations that you haven't seen before, new target location you haven't seen before, the physics-based controller can give you a pretty good initial estimate, and then visuomotor policy comes in to kind of help you adapt that initial trajectory based on the objects that you've picked up. Cool. So Tossingbot was a really fun project, and we were talking to industrial partners, and they were like, tossing is awesome, but what we really care about is placing. So transporter nets was an attempt to try to adapt the dense visual affordance problem framework to placing. And the things that we realized in doing this over and over through teleop is that precise placing really depends on the grasp. So if you took a couple plates and you were grasping each plate differently on a different spot, and then you decide to place it on the same spot, then you'll end up getting a stack of plates that just don't line up. So placing is a form of task-oriented grasping, and what it really needs is to be geometry aware so that you can align corners to corners, edges to edges. And that's part of what transporter nets was attempting to do. The first takeaway from transporter nets is that geometric biases can be achieved by modernizing the sliding window approach. Really how this works is that you compute affordances for grasping. You take the argmax, which gives you the grasping location, and you compute a crop. Then you can take the crop and treat it as a sliding window in which you slide across multiple potential placing locations across the scene. And then that cross-correlation operation just gives you potentially the highest score upon which that would be a nice placing location. So there's the general gist of this here can be shown in this diagram here as well, which is you've got this L-shaped block and you want to put it into the fixture. And the first thing that you do is compute a grasp. And once you have the grasp, you can take the local crops, which are representative of local regions around the object. And then you compute its deep features, and you'll have another network that's computing deep features for the scene. And then you take the crop features and you convolve it over the scene. And the hope of this is to get you this sort of geometry-aware sliding window-based approach to giving you these placing affordances. And one of the things that we found out in transporter nets is that softmax cross-entropy loss is great for behavior cloning, in the sense that you can just treat your entire affordance map or affordance maps as a single probability distribution. And then you can minimize the cross-entropy loss between that and the one hot pixel expert label. And the reason why we only have one hot here is because when you're collecting demonstrations, you might only have one action label per time step before the scene changes. But it's important to note that why this is surprising is because the true distribution is likely multimodal. So if you have multiple good placing spots in the scene, or if you have multiple objects that are available, you're very much likely the true distribution is going to be multimodal. But what's interesting was that with transporter nets, is that even with this particular loss with one hot labels, you end up still being able to capture these multimodal distributions. So one example is that if you wanted to place this disk into this hole inside of the kit and you had an off-center grasp, then the set of placing locations that exist in SC2 would appear as a spiral. And so here, this is a visualization of the affordance map of SC2, but it's collapsed against rotation so that you can visualize it as a donut. But the point here is that this is a multimodal distribution and this is output from transporter nets that's capable of achieving this kind of representation of actions. I thought was really cool because you could also have the letter E and you have multiple letter E's that you need to place into the kit, but you can capture two possible placing spots that you need to accurately place into the kit. So what we learned from transporter nets here is that particularly in the architecture, the visual features provide a strong inductive bias for learning these modes. Presumably the fact that we're able to capture this spiral in SC2 is because the features are all lined up and they just kind of clicked in the cross correlation. Softmax cross entropy loss is awesome. And what we realize is that if you squint real hard at transporter nets, you realize that it's an energy-based model. And that sort of led to our follow-up work on implicit BC, which is that energy-based models are great for behavior cloning. So here we formulate BC policy learning as the implicit minimization of an energy-based model. And you're taking as input an observation and sampling actions or regressing actions through gradient descent. The key contrast here is against explicit policies where you would typically feed in your observation, which is like an image, and then feeding it through a deep neural net and then out predicting some set of actions that you would minimize the distance to the ground truth with MSE loss. And here in implicit BC, we're learning a probability distribution over actions, particularly with the info NCE loss, which is the same type of contrastive losses that you would get in work in contrastive learning, and also is the same exact loss we use in transporter nets. So the core difference here, and here specifically, this is a strict generalization of transporter nets in the sense that the action space here can be continuous. Whereas in transporter nets, the set of actions is the uniform grid of actions over the pixel space. Yeah, and you can have some pretty awesome demos with implicit BC where you're kind of sorting out the different objects, and the input to the system here is just raw RGB images, and the output are the velocity of the robot. And a key thing to get this demo to work is the negatives that we sample are uniform. An interesting part about energy-based models, and we saw this earlier, or signs of this in transporter nets, was the fact that this loss function can still be able to represent multimodal actions, even though your demonstrations may only come in as one hot. So if you had a drone and it was flying through a forest, say that it was about to run into a tree, you can either fly left or you can fly right. And if you had an explicit policy where both actions are part of your ground truth, then you might just end up regressing the middle and crash into the tree. whereas you want the system to be able to express the fact that there are two paths. And so this becomes, I think, pretty potentially critical for many downstream applications. And another aspect is that you can more sample efficiently learn discontinuous trajectories. In behavior cloning, when you're learning from demonstrations, human demonstrations in particular can be very discontinuous, in the sense that if a remote controller is controlling the robot to move an object, they might sort of stop and readjust their trajectory, kind of also move the robot around just to see or get a feel for the UI, etc. But all of that kind of exists implicitly inside of the data. And so the nice part about implicit BC is that you can just fit the function better. And there's also work in machine learning area on the convergence rate of neural networks for learned functions of different frequencies, just that the eigenbiases of these multi-layer perceptrons have a tendency to learn these lower frequency functions first before they learn high frequency ones. And so the discontinuous trajectories that you see in human demonstrations are high frequency transitions. The nice part about formulating behavior cloning as an energy-based optimization problem is that you can lift your prediction space into one dimension higher so that you're turning it back into a low frequency function problem, fitting problem. An interesting follow-up that we had with implicit policies too is that you start to give rise to better action representations for continuous control. This work was called Implicit Kinematic Policies, and this was by Adi. And the observation here is that in robot learning, oftentimes choosing the right action space can lead to substantial differences in performance when you're, depending on what application that you're doing. So on tabletop manipulation, you might prefer a Cartesian action space, whereas if you're doing locomotion, you might prefer a joint action space. And this is because gates would be defined in joint spaces, and inductive patterns might be more apparent for tabletop manipulation in Cartesian space. And entire workshops have been dedicated to this topic, which is trying to figure out the relationship between action representations for learning and continuous control. People have found that different types of action spaces lead to various types of downstream performance gains. So one of the main ideas of this project was to see if we can just have a unified system that is able to let the model decide what action space to choose for itself. So here, because we now are, at least in the implicit formulation, we now have actions going in as input, you can feed in directly just both, for example, actions in joint representations and the same actions represented in Cartesian space. And then have the neural net figure out which of the spaces it prefers for learning inductive biases. And one of the interesting parts about this is that you can have some tasks which are more Cartesian focused or for tabletop manipulation, like scooping particles and putting them inside bowls. You could have more joint-centric representations where they're using elbows of the robots to pick up objects and lift them and pour particles down into another bowl. And previously, you had to pick either joint space or a Cartesian space to get the maximum performance of each task. But with this formulation, you can get the best of both worlds with the same model. And you can also, a fun application here as well is that you can also put in forward kinematics. Since actions are now input, you can put in forward kinematics as a differentiable module inside of your network so that gradients are passing through all the way from your downstream energies all the way into your action spaces. And the nice part about this is that if you had a robot that had joint encoder errors and you wanted to do a precise insertion task, then you can just incorporate this module and you can, a part of the function, a part of the deep network could be learning weights that are trying to compensate for those joint encoder errors. So I think I'm fairly excited about this in terms of enabling manipulation on low-cost robots. Cool, yeah, and also just a side note is that this implicit formulation, a lot of the things that I've just talked about are things that are also applicable to value functions and reinforcement learning. So I think that it's very exciting to see if we can apply some of these things there too.
So, Andy,
Cool.
maybe
So yeah.
a quick question. So one of the
Yeah.
intuitions I think you mentioned a couple of slides back was that implicit functions are lower, I guess lower rank in some ways, or they require low frequency, or they require to fit a low frequency function. Is there something empirical, or is there something, also more theoretical that one could write down?
Mm-hmm. Mm-hmm. Yeah, there's a bit of theory that's inside of the implicit BC function, but we're just showing that implicit functions can represent a good class of functions. And I think that specifically on whether or not the, like if there's smoothness inside of the energy functions, that we haven't proved. And that was mostly just empirically saying. Yeah.
Okay, thank you.
Yeah. Cool. Switching gears a bit, I think one question about the previous projects is how much data do we actually need? And for projects like implicit kinematic policies, we require on the order of 50 expert demos. With transporter nets, it's roughly the same amount, but this allows you to learn generic, a couple pick and place tasks. And once you scale up the visual complexity of the tasks, you start getting into around 500 expert demos in order to sort these blocks into their corresponding locations. And once you do tasks that are a little bit more contact rich, like trying to scoop the particles and put them into the bowls, then you start needing a couple thousand expert demonstrations to be able to achieve performance around the 80 and 90% range. And it really makes you wonder, as we increase the complexity of these tasks, it just seems like the amount of data that we need to collect just becomes exponential. The second area that I'll talk about a little bit today is how can we potentially improve sample efficiency of systems that we have by learning from the internet. The first project here is learning to see before learning to act. And this was a project by Yen Chen. And if you recall the methods that we had for learning affordances previously, which is taking as input RGBD images and outputting grasping affordances. A lot of the architectures that we adopt in predicting these affordances are carried over from computer vision literature and are classically used in object detection and segmentation. So a very natural transfer idea is to pre-train on some of the large-scale offline data sets that we have, including ImageNet, COCO, and hope that they can help the affordance models. And one of the key things that we found in this paper is that not all data sets or offline data sets are created equal. So specifically on MS COCO, we find that it's capable of better regularizing the type of affordance predictions that our models are making. And it's definitely better than random initialization in the sense that random initialization, your model just very easily overtrains into pockets of the action space that it's seen inside of its data set. ImageNet features surprisingly didn't do as well. And we conjecture that it's because on MS COCO, the models have been trained on object detection. So they have a little bit more spatial invariance to them, whereas the ImageNet features, they're being trained on image classification. And so they're kind of just picking out the most salient features that are in the scene. Yeah, and then if you're, in the case of predicting affordances for suction, for example, suction accuracy oftentimes depends on information related to the surface normals. And so what we also find is that if your offline data set is a data set that's very much related to the task at hand, so in this case, we pre-trained on surface normals and then fine-tuned on downstream grasping with suction, we can find a performance boost increase. So here was mostly talking about taking existing computer vision data sets that people have already created and trying to make use of that. The next project, XIRL, talks a little bit more about how can you learn from internet scale videos, for example, YouTube's. And the key takeaway here is that learning from these third-person videos from YouTube may require embodiment agnostic methods in the sense that the way that a person does a task is going to be very different from a robot. So we've seen some awesome work in the area where we have videos of humans doing a task paired with robots doing the same task. Oftentimes they're doing the tasks very similarly. However, if you think about it in the long run and we want robots to be able to watch a YouTube video of a person making sushi, then your robot's gonna have to figure out how, well, at least your robot's going to be making sushi differently. So Kevin had this awesome example where the task is to put all the pens in the comp and transfer to another. And at least in the scope of this task, it's you could already start to see that if you tell a human to do the task, they would scoop up all the pens and do it all at once. Whereas if you had a parallel jaw gripper, in order to successfully do it reliably, you might just end up doing it picking up each individual pen one by one. So that results in very different trajectories that you would see. And the goal is to try to use this video to try to learn policies that can do this. Kevin distilled the problem into a simpler, a very nice benchmark called X Magical, where we had these agents do the same task, which is pushing blocks into a goal zone, but they would do it differently because their embodiment is different. So you had a long stick that would push all 3 blocks into the goal zone at once, or you would have a smaller agent that needs to push it one by one. And the point is that the way that the demonstrators are doing the tasks are different from the learner and also different from each other. And the question is, can we capitalize on the fact that these demonstrators are doing the task differently from each other? If you visualize the trajectories of these agents doing the task, you'll realize that some trajectories are short, some trajectories are long. And one key question that we had here is, from visual features, can we learn to fold these trajectories on themselves in a way such that we have this new state, latent state representation that captures some notion of task progress? So that was the main motivation behind this work. And it turns out that there's actually a body of literature in self-supervised learning in computer vision that has been looking at this exact problem in the scope of video understanding. And in their tasks, they've been looking at video alignment, but here we can think of trying to use the same kind of method to align the videos of the demonstrations that we had coming in from different embodiments. So that technique is called temporal cycle consistency. And you're ultimately trying to self-supervised learn features such that you can, from these features, they're informative enough to help you learn a generic visual reward function. So the approach here is we take demonstrations from different embodiments, and for one episode coming in from one embodiment and another episode coming in from another embodiment, we can take one video frame from one demonstration, compute the visual features, compute the soft nearest neighbor to the video frame of another of the other episode, and then match it back against, and then compute the soft nearest neighbor of that soft nearest neighbor, and then try to minimize the consistency loss between the two. And this self-supervised objective ends up helping us do that folding of trajectories that I talked about earlier. And what you can end up doing now is taking a goal image, computing the visual features in this space, and then using the distance to those features as a way to compute rewards for RL. And so generally, we show that if you use this for RL, you end up getting better performing policies on the downstream task. And you also improve on sample efficiency. Cool. So this next project that I'm going to spend a bit more time on is called Socratic Models, and it just came out on arXiv recently, and I'm very excited to talk about. In the previous 2 projects, I talked about improving robot learning with internet scale data, and we can do this either by pre-training on existing offline data sets, or we can see if we can successfully learn from videos like YouTube. This last category here, or this next project, is focused on how can we give robots access to information from the World Wide Web through foundation models. And this project is called Socratic Models. And recently, we've seen these really amazing capabilities coming in from these foundation models, including large language models like GPT-3 or visual language models like CLIP. An interesting observation to note is that for models like CLIP, visual language models, they're trained to map images and text into a shared embedding space. And they're often trained on the scope of captions or alt text HTML that you find on the internet. But the thing is that large language models have been trained on so much more data than just captions. They've been trained on fictional novels, test questions, spreadsheets. And so the thing is that these different foundation models, they're capturing very different but very unique capabilities. And in this paper, we're talking about how these capabilities can in fact be very complementary to one another. So if you just took these zero-shot foundation models and had them interact with each other, you could potentially get some really awesome new multimodal capabilities with guided Socratic dialogue. What we mean by Socratic dialogue is, so first of all, this is an analogy to the Socratic method, which is a teaching method where the teacher engages in argumentative cooperative dialogue with students in order to come to a shared consensus or conclusion about a problem that they're both thinking about. And the context here is that we're trying to apply the Socratic method for these foundation models. And the thing is that because these foundation models are all grounded on language, they can use language as the common denominator by which they communicate with each other. So say that you have a visual language model, it can try to give you rough guesses for what are the object entities that it might see in an image. It'll pass that to GPT-3, which can then reason about, oh, what is a potential, for example, image caption that I can generate for this, and then pass that back into the visual language model to have it rank which one is the best caption. And it turns out that you can get some pretty exciting results on image captioning just with a really simple zero-shot framework like this. There's this image of 3 folks and an elephant, and the example caption that's being generated here from the system is the 3 people in this photo appear to be enjoying a close encounter with an elephant. This majestic creature looks like a gentle giant, and the handlers seem to have great rapport with her. What a fun and unique experience for these tourists. GPT-3 is fairly creative in this one. The way that it works is, at least for this image captioning example, we have several other examples too. You can take a clip and GPT-3 and you can formulate it as sort of this structured dialogue that is being scaffolded by prompt engineering. So the first thing that, in order to caption this image, which comes as input, it might go through this intermodal dialogue, and the parts that are green are highlighted in green are coming from clip, and the parts highlighted in blue are coming from GPT-3. So here, clip might, by ranking object categories from typical data sets like open images or Tencent ML images, you can rank those object categories against the image to find the top matching ones. And you can list them all out. Just say that, you know, this could be a dining room, or this could be I maybe see a sliding window, maybe a breakfast area, and then ask GPT-3 to say a create short caption that I can generate to describe this image is, and then do text completion. So GPT-3 generates a bunch of different captions, and you can generate 10, 20, 100 if you have the compute, and then just have it re-rank all of those captions against the image. And then you ultimately end up with a caption that, at least when we ran this one time, we got this image shows an inviting dining space with plenty of natural light. You could also do a lot of other tasks in egocentric perception too. So egocentric perception, we chose this domain because it's pretty hard in computer vision. And also it's pretty related. If we were going to have home robots, they're probably going to be cameras located on the head. Well, maybe depend on the system. So we're able to show that you can do video search type problems. You can do image captioning. You can do forecasting of future events with this framework. You could also do, and I'm particularly excited about this, is freeform video Q&A. So you can take in a video as input, and you can ask it questions about the video itself, like when did I wash my hands? I last washed my hands at 3:38 p.m. And the way that the freeform video Q&A works is that you can essentially formulate video question answering as a reading comprehension problem. The key idea there is that through Socratic dialogue between the models, you can generate, take the video and have several key moments inside the video, and you annotate those videos with the captions that are being generated from Socratic dialogue. Now you have those captions, then you can append them together in the form of a generated language-based world state history from video. And this, you can think of this as kind of a short story that you can give to the large language model as context to have it start asking questions about. So you can ask questions like, where did I leave my remote control? I left my remote control in the living room. And then you can also ask GPT-3 to explain its responses. So you can say, this is because, and then it'll say, I was watching TV in the living room and I needed it to change the channel. But yeah, this whole idea of applying on egocentric perception actually becomes, turns it into rather than, the issue with trying to tackle egocentric perception originally end-to-end is that you might struggle in trying to transfer, pre-trained features from third-person data sets. However, here, the switch from third person to first person is just a language from this person versus I am doing something. And so I felt that this was pretty compelling, which is taking a classically hard problem and putting it onto something that we know will work. So given that we do have a little bit of time, I figured that I could do a little bit of a quick demo. I want to see if I can share another tab that I have. Can folks see this tab?
We still see your slides.
Oh, all right. Can people see the egocentric video example?
Yes.
Cool. So this is a YouTube video that's taken from a YouTube star, Cody Wanner, on egocentric. He had done this amazing job of capturing this beautiful video where you have egocentric footage of him doing various tasks throughout the day. And one of the things I like about this particular example for this demo is that he does this, and all of the footage that he's collecting is very organic. And it sort of just shows him, the title of the video is self-quarantine. And so he's just basically doing various activities in the home. So he gets up in the morning, makes coffee, watches TV, working out, taking a shower, working on a desk, and yeah, chopping wood, and also enjoying Netflix with his wife. So the examples that I'll show will be running on this video as input. And the way that it works is that you take several key moments throughout the video and you can generate an image-based caption of each of these key moments. So particularly here, he was receiving a package from DHL. And the summary here just says, I am receiving a package. And this is from back and forth dialogue between Clip and GPT-3. And then he goes on and washes his hands. And then he goes on and does something inside of the kitchen, cooking in the kitchen. But the point of all of this is that through these key moments, you can aggregate them together to generate this activity log, which serves as context for question and answering with GPT-3. And these are just timestamped with fake timestamps, just to show that it works if you did have the real timestamps for the videos. And then now you can do some really cool open form question answering tasks. Yes, you can also summarize your day. So you can say like, oh, I am mostly just doing normal activities like getting dressed, making coffee, watching Netflix, chopping wood. So yeah, freeform Q&A, we can type in whatever we want here. We could do things like, where did I leave my mug? And it'll try to generate an answer. I left my mug on the kitchen counter. I was making coffee and tea and I needed a mug to drink from. Did I drive today? So one of the nice parts about formulating this as short story Q&A is also those classic problems in video search. One of the common issues is that if you just did a nearest neighbor search of frames, you would always get a positive and you don't know when to have a negative. So if you say, did I drive today? Cody didn't drive in his video, but it might just give you the image that matches most closely with a car. So this example is just showcasing that you can actually have a system that tells you, no, you did not drive today. You were home all day. You can say like, when did I watch Netflix? And this is sort of temporal anchoring. This is useful for the types of questions that need to rely on timestamps. And the system can just say, I watch Netflix on television in the living room at these times, and I saw the object television in Place's living room at those times. What did, or maybe we can ask a question like, why did I go to the front porch? And we know that he was receiving a package. It'll say, I went to the front porch to receive a package. I saw the package, was on the porch, and I wanted to get it. I'm not sure if this explanation is actually reasoning about the video. So there's a fair bit here, which is you've got a mix of GPT common sense priors with the actual information that's in the context. And so trying to better disentangle that, I think, would be interesting. You can also say, why was I in the living room with my wife this evening? We were likely watching Netflix together. We were both in the living room at the same time, and Netflix was on television. Cool. So I think that what I'm fairly excited about in terms of these kind of new question answering capabilities, in addition to egocentric VQA, I think that we're also capable of getting some quantitative metrics out of this too. In classic video understanding tasks, there's this popular benchmark called the MSR-VTT. And there's methods that are trained on the data set itself before actually testing on the held out test subset. And we're showing here that you can do a very simple version of Socratic models, which is just augmenting clip, which gets around 27% on this. You can augment clip with information that you get from audio inside of the videos. So you can simply do this by running an audio language model that can transcribe the video for you with speech to text. And then you can have GPT-3 summarize it and then use that to re-rank your clip features. And it turns out that for the video to text retrieval, and R at 1 means that you're fetching the right caption for the video. That ends up increasing the zero-shot state-of-the-art all the way to the right here, which is pretty good against the state-of-the-art methods. And it's important to note that at least for the subset of which we do have transcripts, where the audio has sufficient information or speech inside of it, this number actually goes all the way up to match state of the art. So I think that we can get a lot of mileage just by taking these large language models and finding out what other cool things that we can do with them. So the last slide that I have on Socratic models is I think that I'm really excited about building reconstructions of visual world with language for our robots and AR assistants to use. I think that when I first started my research career, I worked on 3D reconstruction, and the natural response to why this was important was that it was going to be used in robotics. But I'm starting to think that we can think of reconstruction representations in addition to just 3D meshes or 3D point clouds that we're generating. We can also start to think about reconstructions in the form of language. And the reason for this is that, at least in downstream robotics tasks, this might allow robots to actually interface with the models that are trained on internet scale data that store common sense knowledge. And so I'm coming back to this diagram here because I'm excited about the fact that we can show these really cool multimodal capabilities with these foundation models interacting with each other. And I think that we have a potential here to take these robots, which have control algorithms. If we can ground those control algorithms on language, then we have a natural interface to tap into some of the awesome things that these foundation models can do. So this just starts off with I think we can start off by just looking at or thinking about reconstruction representations or other perceptual representations in the form of language. So I'd like to conclude with this slide here, which is just my general thoughts of where I think robot learning is headed. With Socratic models, I think we've shown some exciting new zero-shot perception capabilities. And I think that recently we've also seen some really exciting work on zero-shot planning, for example, from Berkeley and Google. And I think that these things, at least in the near future, in my mind, is going to start coming together in terms of potentially improving the way in which we think about the recipe for robot intelligence. So I think previously we've always thought that in the scale of robot intelligence, we're going to collect sufficient data in order to reflect the types of intelligence that toddlers have. And then by increasing and scaling up the data, we'll eventually achieve common sense. And I feel like this arrow is not going to be a one direction arrow. I think, in fact, in the near future, we might start to see that internet scale data actually helps to come and meet us halfway and giving us some of the common sense information that we might find. And I really hope that this will be something in which could really help us achieve, better embodied AI in general. And I really hope that, at least based on these exciting results, I'm really excited about what is to come. Cool. And with that, I'd like to thank all of my collaborators with whom I've been very fortunate enough to work with, and also special shout out to Pete Florence, with whom we've been back and forth thinking about ideas on these things for a long time. Yeah, and that's all I had.
Well, let's thank Andy for the wonderful talk. So we have, a few minutes for questions. So if anyone wants to go. So I guess maybe while people are warming up to questions, Andy, maybe I can start. So,
Yeah.
I really like the way you presented about your vision for embodied intelligence, right? And then, so on one side, it seems very cool, and it seems like, we are very close in, getting a plan, right? But then, once you touch physical robots, you realize it's like, pick up the cup is actually a very hard operation, right? Because the cup might be behind a box, the handle may not be visible, blah, 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 blah. So I'm wondering, what's your perspective on how much can internet scale data, help us solve some of, these hard problems at the low level manipulation?
Yeah, that's a great question. And I think that, for example, if you wanted to grasp the cup and the cup was behind a box, I think that there could be some mileage be gotten immediately just by having like a language image model like Clip, for example, tell you I see a cup or I don't see a cup, and then just see what the scores are. I feel that we can take some of these interesting capabilities where whenever we have a new task and we have either a language description of the task or some sort of grounding of the task in language, then we can play around with seeing if we can get some of the functionalities or common sense functionalities that we hope these robots to have originally. We can then bake them in with the foundation models. So I think there's quite a bit of mileage that I think that can be gotten just by doing something like that.
Great. Yeah. Any questions from the audience? No. So maybe I'll follow up with one more. So we saw all these cool results about zero-shot perception. So can you comment on maybe some of the failure modes of these models, or what things they don't get right?
Yeah, absolutely. So there's many failure cases. And I think the most common one is that if you don't have enough information inside of your short story or whatever you've provided in as context, then you won't be able to answer the question. So in the paper, we go into a bit of a discussion on this, but when you have your video input and you're sampling various key moments, you could either sample the key moments uniformly, or you can use some other state-of-the-art computer vision techniques. But the choice in which how you sample that key moment determines exactly what's going to appear as context to your system. And so if you end up, for example, saying what did I have in my drink, or what did I have in my margarita on Sunday, that piece of information needs to appear in the context for it to be an accurate response. And GPT-3 might just make up something on the spot that's not accurate. So figuring out when those failure cases happen, and also how we can more accurately address the key moment fetching problem, I think will start to see a better way of like fetching robot memories correctly or something.
I see. So you're saying that we don't really know when GPT-3 makes something up versus when something is actually present. And I guess that's hard to disentangle.
Yeah, exactly. And for a problem like image captioning, that is less the case because you have this re-ranking with the visual language model. So you're kind of relying on the common sense of the model trained on captions itself to actually generate good captions. So if there was some equivalent for that in video question answering, I think that could help.
Great, great. So I think we are at the hour. So let's thank Andy once again for the wonderful talk. Thanks, Andy. And also thanks for making the time to meet with folks one-on-one. Do you have link for that, Andy?
I don't.